All right, so now I'm actually recording this. Yeah, thank you for telling me for catching that and telling me to record it. I apologize to the people who are watching this online and are watching this after the fact, and it's jumping in the middle of it. Um, it's just gonna have to be that way for now. Maybe I'll re-record it someday in the future. The notes will still be available up on my group's website, but it might make it a little bit cryptic to watch the video, unfortunately. Um, all right, so again, we were discussing the second moment of this free energy of this the variation of the Helmholtz potential. And so we know that if we take one derivative of the potential with respect to this external field, we get the average density. So we know that this is equal to d average rho hat of r presence of j of r prime. And what this gives us is a the something like the 2-point correlation function. Right, so it's the 2-point density distribution function. And this is, of course, going to be related to the static structure factor of the system. And so that's kind of the key relationship that we're going to be building out. And because this relationship is invertible, the relationship between J of R and rho of R, that also implies, because of invertibility, because this relationship is invertible, then we can also say that the J of R d rho hat of R prime in J is just 1 over this coefficient. And that's actually going to be the thing that we're going to be able to derive, rho hat of R prime to the -1. Okay, so, all right, so the next thing that we're going to do is to use a Legendre transform to go from this Helmholtz potential in the presence of this field J to something that's a functional of the density, of the spatially varying density field, or the average density. So now we're going to use a Legendre transform. Right, and so I'm just going to use f for that Legendre transform variable, and it's going to be of average of rho. I guess I should make this average of rho hat, and we're going to define this thing to be a of j using the usual Legendre transform definitions minus integral dr j of r, and then derivative with respect to j of r. And of course, this derivative is the thing that we've shown up above, is that's equal to the average density, right? So this is equal to a of j minus integral dr j of r rho hat of r. All right. And we can look at again, we can look at the different coefficients of f by examining df by d average rho hat of r. And so since this depends on j and not the average rho hat, and the only place where rho hat shows up is over here. And so if we take d by d rho hat of that, the only thing that we get back is just simply minus j, right? So this is just minus j of r. And this is the kind of symmetric relationship that you should expect from a Legendre transform. And so this should be, in a hand-waving sense, hopefully familiar from even classical thermodynamics, where there's this symmetric relationship between the derivative of the total energy of a system with respect to the entropy that gives you the temperature. And then if you do the Legendre transform to the Helmholtz potential and you take the derivative of the Helmholtz with respect to temperature, that gives you the entropy, right? And so it's the same kind of analogy that we have here. All right. And the thing that's going to be useful for us, though, is that this, if we take a second derivative of f, so if we do d squared f d average rho r d average rho hat r prime, and because of this relationship, this is going to give us minus d j of r d average rho hat r prime. That's just using the thing from the line above. And from way above, this is going to be equal to our rho hat of r prime, right? 1 over that. And that's from that inversion property. And so the key thing here is that if we have f of rho expressed as a power series in rho of r, the quadratic term is going to be related to this 2-point density correlation function, which is the static structure factor. Right, so as a power series in rho of r, the quadratic term, right, the coefficient of that quadratic term is going to be related to S of k, the static structure factor. Right, and then what we'll be able to do is use some of the field theory stuff that we've developed to see how like the interactions and the structure of the fluid that we're considering are actually reflected in this S of k. And so the interactions will show up. Right, so the interactions are going to be reflected in S of k. And we can also, the other important thing and the really probably the most useful application of this is that the stability of the homogeneous phase. So in other words, if the system does not want to phase separate, the stability of that homogeneous phase is also going to be can also be assessed from this quadratic term. Right? So stability of the homogeneous phase and so if and for example, if this coefficient is less than 0, then that means that this free energy is going to have a negative curvature and it's unstable. Right, and so that's going to be kind of the key mark that we're going to go for to understand when a system is going to be stable or unstable. And so now the thing that becomes our goal is figuring out how we can calculate this quadratic term, this quadratic coefficient. And this is where we're going to use the field theory models. Right, and so now we're going to use field theory, these analytic approaches that we've been developing to calculate this quadratic coefficient. And so we're going to run through that with the Edwards model. So this is the first polymer field theory model that we developed, where we had just a Gaussian chain that had its own self-repulsion built into the model, and then now we have to trace through the particle to field transformation. It doesn't really change very much, but in the presence of this external field. Okay, and so I'll call this model A, or the Edwards model. Right, so if you remember, we have our polymer chains of length n. They have Gaussian bonds along the backbone, so our bonding potential is some I to n, some s to big N, 3 over 2b squared, ri s minus ri s plus 1 squared. Sorry, it should be n minus 1. And then we have a non-bonded potential, beta u1, that is u0 over 2. It's just a local contact repulsion, right, rho hat of r squared. Okay, so then we're going to use the Hubbard-Sturtanovich transformations. Right, so we use those Gaussian functional integrals. So we use the HS transforms. Then with the field J of R also added. right? So our total partition function, right? So our z of j is z0 e to the, or dr to the n e to the minus beta u0 minus beta u1, then minus integral dr j of r rho hat of r. Right, and so now when we run through the whole Hubbard-Stratanovich transformation, everything basically proceeds the same, except we're only going to focus on these terms for the whole particle to field transformation, and we end up with the exact same terms as a function of the field coordinates. The only thing that's different is that when we isolate the particles and turn everything into this molecular partition function, the field is going to be augmented with J of R, right? And so I'm not going to go through the details through all the work of it, but the final result that you get is, with a slightly different coefficient. We will have some path integral over the new field configurations, e to the minus h of w and j. And of course, this is still equal to, our Helmholtz potential. And then the whole structure of the thing is now 1 over 2u0 integral dr squared minus n log q. And I'm going to call this field that goes into this molecular partition function just mu. And now mu of r has the original part that we had when we did the original Edwards model, but now it's augmented with J of R. Right, so we have this extra contribution that we're throwing on here at the end. And of course, we can recall that our Q of mu is just simply 1 over V integral dr little n big N e to the minus mu of Rn bond transition probability between n and n minus 1, and so on, all the way down the chain until we get to the last guy. And of course, the bond transition probability thing is just the, our Gaussian. And so the way that we're going to continue to develop this is that, and this is where the math kind of takes off, and we're probably going to stop in a moment so that we can just come back to this next time, is we're going to write out the mean field equation. So we can use the mean field equation. Right, so we'll say that this occurs when we have dHdW equals 0, and we can derive this guy. So if we take the variational derivative of this effective Hamiltonian, so the first term just gives us a W of R over U naught, so we'll have 1 over U naught W of R. And then the second term is going to give us the density operator. So we'll have I. So the I comes about because there's this prefactor here. And then we'll have our density operator, which is the derivative of Q with respect to IW, or with respect to W of R. But now this thing still depends on W and J. Right? And so I write this as, it's a function of R, and then the semicolon, then this is a functional dependence on both this auxiliary field that we've introduced and the chemical potential field W that came about from the Hubbard-Stratanovich transformation. Right? So it has this extra field that we made up that we're introducing to help us bias to get a particular density field, and the field that comes about through the interparticle interactions. And what we're going to do next time is go through the form of the weak inhomogeneity expression for for the density operator, and we'll be able to develop a relationship between these two things. Right? So next time we'll use the weak inhomogeneity expansion on rho tilde, right, to relate W of R to J of R. And then from there, we'll be able to get this quadratic coefficient that we now know is related to the static structure factor. And we'll kind of see how the interactions bear out through that transition. So yeah, I guess this is going to be my stopping point for today. Let me see. I think this is basically everything I wanted to go for. If there are any questions or points of discussion, I'm happy to hang around for a bit. But otherwise, we will have a short one today and pick up with the rest of it next time when we'll finish this stuff out. All right. Well, everybody have a good one and stay safe out there.